Hello folks, today I'll be tackling a problem called combination sum. This is on the platform LeetCode. I've been kind of liking this platform besides HackerRank. There's plenty of other coding platforms. So the reason I wanted to tackle this today is because I want to get practice with dynamic programming, and this was one of the problems that kind of stood out to me. I've always kind of struggled with this idea of like combinations and permutations, so that's why I want to focus on this one today. So as usual, I'll cover the problem, I'll give you some time to do it on your own, and then I will show you my solution afterwards. So here we go. Combination sum. Given an array of distinct integers called candidates and a target integer target, return a list of all unique combinations of candidates where the chosen numbers sum to the target. You may return the combinations in any order. The same number may be chosen from candidates an unlimited number of times. So two combinations are unique if the frequency of at least one of the chosen numbers is different. It is guaranteed that the number of unique combinations that sum up to the target is less than 150 combinations for the given input. Here's an example. So if you have a list of candidates 2, 3, 6, and 7, and we're told that again these are unique numbers in here, and a target that's supposed to sum to 7, the output we would expect is effectively like two sets of numbers, 2, 2, 3, and 7 all by itself. All right, so that's the problem. I'll give you some time to do it on your own, and then we'll come back with my solution. All right, so my solution involves a dynamic programming list effectively, and the way this will typically work is to have some kind of data structure or list, something like that, where you're building your answer up from previous smaller answers. So what I mean by that is if I'm looking at a target sum of 7, then I can use other target sums like target sum 3 and target sum 4 to make that 7. So having a list that we're building upon is helpful in this regard. And so we're going to start off with 0 and build all the way up to 7, or any n number really, if you think of it like that. So here's the idea. We have our candidates. This is the question example. So we have all these candidates and a target sum of 7, and the answer that we're looking for is 2, 2, 3, or 7. And the thing to keep in mind is that we're dealing with combinations, which mean that the order doesn't matter. So 2, 2, 3, and 2, 3, 2, and 3, 2, 2, that all is saying the same thing. It's a set. It's like a set of numbers. All right, so the place we would start with is 0. If we were to build up to 7, we first start with 0, and the solutions that we would have there would be none. There are no numbers that come up to 0. So let's start off with an empty solution here. There are no solutions that could possibly fit this criteria. We could just like loop through each candidate and just see, okay, can I meet this sum or not? So right now there are none. So I'm going to say, this is another empty list here. What about 2? We can loop through 2 and we notice, okay, 2 actually has a value directly. It can meet the criteria. So we can fill this in with a single 2. 3, 6, and 7 can't match that. And then we go on to 3. 3, we see, okay, there's an actual 3 in there. So we put a 3 in here. Now we get to 4. So here's where things get interesting. So we'll look at this sum of 4. And when we loop through our candidates, what we're doing is we're saying, okay, well, if I'm supposed to sum up to 4, then I can loop through each candidate, and I'm going to look back and say, okay, I'm starting with 2. Well, in order to get to 4, I need to start off with 2 already. So I can actually look back here and just add 2 to whatever is already there, because those are solutions that total 2, right? So all these solutions that are in here, I just add another 2 to it, and I will get 4. So that is us using prior information that we're building upon. And so here I'm using literally like this 2 from here. I'm just adding another 2 to it in order to get this. And I now have a solution for 4 based on previous information. I would go to the 3, and the 3 would say, okay, well, I need to look up. I need to look back to 1 and add 3 to any of those solutions. Right now there are none in here. So this is like an empty set. There's nothing nothing to add that would sum up to 4. So even though 3 it would be able to consider something from prior information. There's nothing there, so there's nothing to add here. If there was like a 1 or something in here, then I would add to this. 6 and 7 are too large, of course, so we're going to ignore those. We go to 5. And here's something to note here. We can loop through it once for the 2, and then we'll say, okay, 2, I look back and I need to add a 3 on, and so I can take this 3 and then add that on. So you might think, okay, it's going to look something like this, where I do 3 and then 2. 3 being from this step over here. Well, that's us going just using this 2. What if we go to this 3? Well, it's going to say look back at the 2, which is here, and then add 3 to those. And so we would be doing the situation where we're like creating another kind of duplicate set like that, which is problematic, right? Because these are basically saying the same thing, and we're dealing with combinations. So this is something to keep in mind. We're going to need to ensure that we don't like kind of run over information that we've already considered. So that's something we're going to have to include in our logic, which I'll show in my code. But for now, assume that we have some logic in place that ensures that we don't duplicate information. So in this case, I'll keep it like this. So we'll ensure that we only keep unique combinations. And then we go to 6. 6, there are a few options here. So if you go to the 2 will look back to the 4 and say I'm going to add another 2 onto that. So that's 2, 2, 2. You have the 3, which has another 3 here. So we just say 3 and 3. And of course the 6 is all by itself. When we loop through it here, we have just a 6 all by itself. So that is how we're going to eventually build up to our final answer. And I'm going to show you how we're going to instill that logic to ensure that combinations are actually unique. Okay, so what do we do? First, I want to create my dynamic programming list, and it's going to be empty basically. So what I'm going to do here is I have some list comprehension, but what I'm basically doing is I'm filling out the entire list based on the target, because remember the index is basically based on the target. So I want to go a little bit, I want to go one more than the target. That's why I have this range for target plus 1, because I want to include the 0 as a place to start off with, just as a basically an empty list. And I'm going to instantiate each element in that list as an empty list itself. And then what I'm going to do here is I'm going to initialize the target of 0, the very first position, as an empty list all by itself. So here's how we prevent going over ground we've already passed. First, we loop through each candidate itself. So in our scenario, that's like looping through 2 first and just like filling in our dynamic programming list just based off 2. Then we'll go through 3 and then 6 and then 7. And when we go through those, then we can use prior information that we're building upon. And what does that look like? Well, for each candidate, then we will go through all targets in the dynamic programming list. And what we will do is we'll look up the previous complementary values. So in the case of like 5, for example, if I'm currently looking at candidate with the value of 3, then I want to go back and look at what value was at 2 and look at all those combinations and then just add 3 to them basically. And so that's what I'm doing here. So I'm basically going for the value in range, the candidate. So why do I start with the candidate and not like 0? Well, there's logic to that, because the thing is, we saw this before where if we're looping through like 6, then we don't care about values at 2, 3, 4, or 5, because 6 can't sum to those values. We're told that all the numbers are positive, so we can't actually sum to anything less than 6 anyway. So why start from there? We might as well just start at 6. So that's the idea. So we're going to start at 6, or whatever the candidate is, and then go up to the target plus 1. I'm doing target plus 1 because range is a exclusive for the last value, so we want to make sure to include the target, the literal target value. So by doing that, what we'll do is we'll create the complementary value, and you're going to pull that out, and you're basically saying previous solutions is what we're looking at. Those are the previous solutions from that position. from the complementary position. And what we're doing is we're going to loop through each solution, and in doing so, I'm going to add the current candidate to those previous solutions. This is just creating a new list. So this part that I have highlighted is just creating a new list. So I'm not like modifying what's already there. I'm literally creating a new one, and this whole thing is a list comprehension. And what I'm going to do here is I'm going to append those combinations to whatever my current value is in the dynamic programming list. So this looks all very abstract and weird, so let me go through an example. All right, so when we start that loop, we are basically beginning with this scenario where everything has an empty list within the list. So it's like a list of lists, so I want to keep the nesting in mind for this. Previously, I wasn't doing that, but now that we're in the weeds of it, I'm showing the whole thing. So what's happening with the first position is that it has a nested list that is empty, which means that there's like a solution here, but there's nothing in it. And this is going to serve as like the groundwork for anything that kind of refers back to the 0 position. So what does that look like? So when we go through the list, we first go through candidate 2, and we go through the whole list using only candidate number 2. So candidate 2 comes in, it starts out at 2, and it is going to look for the complement, which is to begin with. So remember here, this part here. We're going to loop through the whole thing starting at number 2. So this one will look at the complement, which is going to be 2 minus 2 here, which is 0. And it's going to say, I'm going to add 2 to all of those solutions. There's only one solution, which is an empty list. So we're going to add 2 to it, and we're going to append that to this current list. So that's going to look like that, 2. Then we're going to go to 3, look at its complement, which is at 1. Nothing there, we kind of ignore it. We go to 4, and 4 is now going to look at the complement, which is at 2. It's going to look at all those solutions and just add 2 to each one of those, of which there's only 1, but it's going to look like 2, 2. Then 2 goes to 5. 5 looks up 3. 3, there's nothing there. It looks at 6. 6 looks back 2, and now there's 2. 2, 2, 2. It goes to 7, looks at 5, there's nothing there. So that is what it's going to look like after we've passed through candidate number 2. Here. What happens when we go through number 3? So this candidate right here. It's going to start at 3. It's going to look at the complement, which is currently going to be pointing to 0. It's going to add 3 to all those solutions. So it's just going to look like that. It goes to 4. It's going to look at 1. Nothing there. It's going to go to 5. And because it's number 3, it's going to look at complement, which is that 2. And it's going to add 3 to that. Okay. So then we go to 6. 6 is going to look at its complement, which is at 3, and it says, okay, I'm going to add 3 to all those solutions. So it's going to then append all those additions to this list. So we're going to get 3, 3. Then when we get to 7, it's going to look at the complement, which is at 4, which has 2, 2, and it's going to add 3 to those, which is 2, 2, 3. And so now so you can see how we're ensuring that we're not going over ground we've already seen, because the only time that 2 gets to be considered is its first pass. Then we go to 3, and then it gets to consider everything, and we're building on that iteratively. And this helps ensure that you're only seeing one combination one time, basically. So I'll go through 6. So 6 starts at 6, so it's kind of easy because it's just itself. And then 7, same thing. It points to 0 and sees nothing, and it's there. And so by the time we get through the whole list, we'll have this as our dynamic programming list. And all we have to do at the end is just look up position 7. What's your solution? What are your solutions? And that's what we're doing. And so that's basically it. And so let's run this code and see what we're doing here. We get accepted. Let's submit. Okay, it looks like the submit was accepted as well. You get a success screen here, which tells you like how fast it was running compared to other people and whatnot. Okay, so let me go back and do some time complexity. So first and foremost, we are looping through all of the candidates. So that is something to consider. I'll call that big O of n, n being the number of candidates. So that's one for loop. The other for loop here is that we're looping through from 0 up to the target. So I want to consider this to be big O of m, but that's just a different number. So we have m of m. One other thing to consider, this is kind of somewhat minor, but worth considering. The fact is we're looping through all the previous solutions. So technically there could be at most n solutions, even though it's like it tapers off. It's very unlikely for that to happen. But anyway, technically this is big O of n possible solutions for that, previous solutions. But I don't think that's too much. It's not going to truly factor into the equation. Time complexity equals big O of n times m times n. Yeah, so this looks worse than it is, and you can probably correct me on this because I believe this is the case here. Because of this list comprehension, we are looping through all previous solutions, of which there potentially could be at most n solutions. The only time that happens is once you've gone all the way to the very, very end for that to even happen. So even though that's like a consideration, this one truly isn't really affecting it. What we're dealing with is probably more realistically big O of m times m. So that's what I'll stick with for now. All right, folks, that is it for today. And if this is the kind of content that you like, make sure to like, subscribe, and do all the good things. And I will see you next time. Take care.